Welcome to Ask and Learn.
All right, we're using conservation of energy throughout this problem. Essentially, you have spring force or elastic potential energy of the spring, gravitational potential energy, and no kinetic energy. So in the first part, part A, you're looking at when the block is not attached to the spring, looking at initial potential energy or spring energy, elastic potential energy, to be equal, and you set that equal to gravitational potential energy, the top, or at whatever height it reaches. And so initial elastic potential energy is 1/2 kx1 squared, x1 being the initial displacement of 0.5 meters. Gravitational potential energy that this is converted to is mg times d sine theta. And the reason this is y, and y has to be, sine theta is y over d, right? So this d is what we're interested in. Therefore, d sine theta will give us y, which is why this turned out the way it did. Therefore, d is what we're after, is 1/2 or kx1 squared over 2 mg times sine theta. Okay, and k is 75 newtons per meter. X1 is 0.5 meter quantity squared over 2 times 2 kilograms times 9.8 meters per second squared times sine theta, which is 41, giving us a d of 0.73 meters. In part B, we have initial elastic potential energy is equal to gravitational potential energy at the top, let's call it UG2, plus the elastic potential energy at the top, so UE2. Okay, in other words, 1/2 kx1 squared is equal to, again, mgd sine theta, plus 1/2 k times extension squared. So this would be d minus in a x1 quantity squared. So let's plug in some values, make things easier before we solve the quadratic. So this is 1/2 times 75 times 0.5 squared is equal to 2 times 9.8 times times 0.73 times sine 41, plus 1/2 times 75 times d minus 0.5 squared, whole squared. All right, so looking at the quadratic on the right-hand side, you have 37.5 d squared minus 37.5 d, because that's what the second term from this will give us, plus 1/2 75 times 0.5 squared, which is the same as this term on the left, so those terms cancel. The only other remaining term is plus whatever this gives us, which is plus 0.9 or 9.387. And therefore, we solve this quadratic to get d equals, d has to be positive, remember, so it is 0.66 meters. All right, and in part C, use a different ink here. You have a d of 0.5 meters that's given, and now you have a force of you've work done due to friction. So again, initial elastic potential energy is equal to final gravitational potential energy, but added to that, we have work done by friction. So 1/2 kx1 squared is equal to mg d sine theta as before, plus mu sub k times the work done due to friction is force of friction times d. So this is force of friction times d. So this is mu sub k times normal force times d. And normal force is mg cosine theta. times d. Okay, so we want mu sub k, and so you can take the mgd terms common. Mgd times sine theta plus mu sub k cosine theta is equal to 1/2 kx1 squared. Therefore, mu sub k, mu sub k, excuse me, mu sub k cosine theta will be kx1 squared over mgd minus. Therefore, mu sub k, divide both sides by cosine theta, you get mu sub k is kx1 squared over mgd cosine theta minus sine theta over cosine theta, which as we know is tan theta. All right, now let's plug in the values. We have mu sub k is equal to 75, just k, Newton per meter times 0.5 meter quantity squared over 2 times 2 kilograms times 9.8 meters per second squared times x1 d cosine theta, excuse me, so 0.5 meters cosine minus the tan 41 that we had. And so this gives us 0.40 for the coefficient of kinetic friction, and that's it.